Okay, friends, very good morning. Welcome back to our RFIC classes, unit number 4, Class B power amplifiers. So, here the power amplifier is Class B power amplifier is given, and that particular amplifier, the input waveform and the output waveforms will also be provided there. X and Y power supply, load resistance, transformer 1, T1, uh, T1 small m VDD M1, M2, all these are Class B power amplifier components. So these they are connected like this in the circuit. If the bias were arranged to reduce the fraction of a cycle over which drain current and drain voltage are simultaneously non-zero, transistor dissipation would diminish and improve efficiency. One way is switch off the output device for every half cycle. This operation is called Class B power amplifier. Exact 50% conduction is not practical, so pure Class B does not exist. It produces non-sinusoidal output, but it has good linearity. It produces in push-pull configuration with two transistors. Although the single transistor version of a Class B amplifier is analyzed here, but the most practical Class B amplifiers are push-pull configurations of two transistors. We may assume that the drain current is sinusoidal for one half cycle and zero for the other half cycle. The drain current ID of the form ID is equal to IRF sin omega naught T for ID is greater than 0. And drain voltage and current for ideal class B amplifier is model waveforms are shown here. To compute the output voltage, we first find the fundamental component of the drain current and then multiply this current by the load resistance. I fund is equal to 2 by T integral of 0 to T by 2 IRF sin omega naught T into sin omega naught T dt is equal to IRF by 2. I fund is equal to 2 by T 0 to T by 2 id sin omega naught T into dt. I fund is equal to 2 by T integral of 0 to T by T id sin omega naught T dt is equal to 2 by T 0 to T by 2 IRF sin omega naught T into sin omega naught T dt. That is equal to 2 IRF by T, that is integral of 0 to T by 2 sin square omega naught T dt is equal to 2 IRF by T 0 to T by 2 1 minus cos 2 omega naught T by 2 into dt is equal to 2 IRF by T integral of 0 T by 2 1 by 2 dt minus 1. So it is equal to 2 IRF by T 1 by 2 into T by 2 minus 0 I fund is equal to IRF by 2. Class B power amplifier. V out is approximately equal to IRF by 2 into R sin omega naught T. Since the maximum possible value of V out is VDD, it is clear from above equation that the maximum value of IRF is. The peak drain current and maximum output voltage are therefore the same as for the Class A amplifier. Compute the drain efficiency as before. We first calculate the output voltage as P0 is equal to V0 square by 2R. The maximum signal amplitude across or is V naught is not greater than VDD. So output power maximum is P naught comma max is equal to V square DD by 2R. Class B power amplifier. Computing the DC input power requires computation of the average drain current. ID bar is equal to 1 by T of integral of 0 to T by 2 VDD by R sin omega naught T dt is equal to 2 VDD by pi R. So then ID bar is equal to 1 by T 0 to T by 2 VDD by R into sine omega naught T dt. And then ID bar is equal to 2 VDD by R dot 1 by T 0 to T by 2 sine omega naught T into D2. Next, that is equal to 2 VDD by RT minus cos omega naught T by omega naught T by 2 by 0 to T by 2. So, 2 VDD by RT of minus cos omega naught T by 2 by omega naught plus 1 by omega naught, that is equal to 2 VDD by RT of 1 by omega naught plus 1 by omega naught. 2 VDD by RT of 2 by 2 pi by T, that is equal to 2 VDD by RT to T by 2 pi, that is equal to 2 by 5 into VDD by R. ID bar is equal to 2 VDD by pi r, so that the DC power supplied is PDC is equal to 2V square DD by pi r, so that the DC power supplied is PDC is equal to 2V square DD by pi r. Finally, the maximum drain efficiency for a class B amplifier is eta is equal to P naught comma max comma PDC, that is equal to pi by 4 is approximately equal to 0.785. The normalized power capability of this amplifier is 1 by 8. The same as for the class A, since the output power, maximum drain voltage and maximum drain current are the same. Class B power amplifier. Here the circuit is shown in the figure, and input and output waveforms are also shown, and the VDD input voltage, load resistance, biasing voltage, VDD, filtering matching, RFL, all these values representing circuit also shown here. And next, in class C power amplifier, the gate bias is arranged to cause the transistor to conduct less than half the time. Consequently, the drain current consists of a periodic drain of pulses. The drain current of the amplifier is ID is equal to IDC plus IRF sin omega naught T, comma ID is greater than 0, where IDC is the offset the bias current, which is actually negative for a class C amplifier. Of course, the overall drain current ID is always positive or 0. The drain voltage and the drain current therefore appear as depicted in the figure. Drain voltage and current for ideal class C amplifier model graphs are shown in the figure. The drain current is a piece of a sine wave when the transistor is active and 0 when the transistor is in cutoff region. The voltage across the load remains substantially sinusoidal because it has a high quality output tank. In this, it requires to solve for the total angle over which the drain current is non-zero. We begin by solving for the total angle over which the drain current is non-zero. In order to reduce the number of steps needed to arrive at the answer, we first rewrite the expression for the drain current in terms of a cosine rather than a sine. So ID is equal to IDC plus IRF into cos omega naught t when ID is greater than 0. Setting the current equal to 0 and solving for the total conduction angle 2 phi yields 2 phi is equal to 2 cos inverse of IDC by IRF. So detail of drain current waveform is shown below, which can solve the biasing current as IDC is equal to I minus IRF into cos phi, and also ID is equal to IDC plus IRF into cos omega naught t when ID is greater than 0. This is the condition for what the drain current and the drain biasing current. Compute the average drain current, that is ID bar is equal to 1 by 2 pi of integral of minus phi to pi box minus phi to phi of IDC plus IRF cos phi d phi. So while integrating this term, then the term will becomes is equal to 1 by 2 phi of with respect to phi we are differentiating here, then 2 phi plus 2 phi IDC plus 1 by 2 phi IRF sin phi minus phi to phi. After substitution with the expression for IDC, which yields IDC is equal to IRF by phi into sin phi minus phi cos phi. This is what the calculation part of the class C power amplifiers while derivating the drain current. So class C power amplifier. The average drain current we know that is written as ID bar is equal to 1 by 2 pi of minus phi to phi IDC plus IRF cos phi d phi. 1 by 2 phi IDC phi of minus phi to phi plus IRF of sin phi into minus phi to phi minus 2 pi IDC 2 phi plus IRF by 2 phi of sin phi minus sin minus 5. 5 by uh, 5 by 5 IDC plus IRF by 2 phi 2 sin phi, that is equal to 5 by pi into minus IRF cos phi plus IRF by pi into sin phi. The fundamental term in the Fourier series I fund is equal to 2 pi t into 0 of t id cos omega naught t dt is equal to 1 by 2 pi into 4 idc sin phi plus 2 irf phi plus irf sin 2 phi. Substitute IDC is equal to minus IRF cos phi. We obtained I fund is equal to fundamental current is equal to IRF by 2 pi of 2 phi minus 2 sin 2 phi. Again, the fundamental current component from the Fourier series is written as I fund is equal to 2 pi t 0 to t id of cos omega naught t into dt. Omega naught t is equal to phi, and let it be omega naught dt is equal to d phi. Then that equation will becomes is equal to 2 by 2 pi of minus phi to phi idc plus irf cos phi into cos phi into d phi. Then the 2 will becomes cancelled, and that equation remains as 1 by phi into minus phi to phi idc cos phi d phi plus minus phi to phi irf cos square phi d phi, and it will be written as 1 by phi into idc sin phi to phi plus irf minus phi to phi 1 plus cos 2 phi by 2 of d phi. Is equal to 1 by 2 pi is equal to 1 by 2 pi of minus IRF sin 2 phi plus 2 phi IRF. I fund is equal to IRF by 2 phi minus sin 2 phi. Hence, the fundamental current is equal to IRF by 2 phi into 2 phi minus sin 2 phi. We obtained fundamental current is equal to IRF by 2 pi of 2 pi minus sine 2 phi. The maximum output voltage is VDD is equal to IRF R by 2 pi minus sine 2 phi. The current IRF in terms of VDD is written as IRF is equal to 2 phi VDD by R of 2 phi minus sine 2 phi. And then the peak drain current is the sum of IRF and the bias term. ID comma PK is equal to, hence these two terms will be added, which simplifies to ID comma PK is equal to the following term will be obtained. Okay. For a fixed output voltage, the peak drain current approaches infinitely as the pulse width decreases towards zero. From the above equation, the maximum efficiency of class C amplifier is eta of max is equal to that equation. As conductance angle becomes zero, the efficiency approaches to 100%. Its efficiency is large, but it has reduced power handling capacity, gain and linearity. Eta is equal to I fundamental current by DC current.